Can you guys all see me and hear me?
Yep.
Can you hear me?
Yes.
Okay, all right, thank you. All right, so I'm going to get started. These are the next assignments that are due. The capacitor worksheet, I'm hoping you did like half of it. We'll talk about dielectrics today, and then you should be able to do the second half. I've covered most of chapter 26 already. I just need to talk about energy and dielectrics, and again, I'll be doing that today. Okay, so maybe I should write that on the board. All right, so I'm hoping you can read chapters 26 and 27. Chapter 27, I've kind of lectured through some of it because of the Ohm's Law, not the Ohm's Law lab, but the multimeter quiz. So it won't take long for me to go through that on Wednesday. So anyway, make sure you've read by 26 and 27 by Wednesday, if you haven't done so yet. Pick up your exams. A lot of folks have not picked up their exams, and I forgot and it was my fault. The first group who took the exam, I forgot to give you your exams back. I apologize, but I still have those. Okay. And I have the exams you just took. I will give you the exam key soon. I just got to copy it and send it. This will be the last one I'm actually going to send to you because the next exams and the next time I have an exam will be October 29th. And after October 29th, you're coming here every Friday. And so whatever exam key I post, I'm going to post in a glass case across from my office. Okay? And everything will be handed back to you in person. You'll get something back right away, at least the following week, because we're meeting every week in lab after the 29th. Okay? My concern is the performance on exam 2. I don't know if you read my email I sent last night. I just saw a lot of issues that concern me on the exam. It could be some of it, background, because, people are asking me some mathematical questions where I was kind of surprised at. I gave this exam before. I gave this exam 10 years ago, and the average is much higher. And I'm going to keep doing that. I'm going to keep using an old exam so I can use it as a benchmark to see how this group does compared to previous groups. I did notice some concerns regarding math in terms of what you remember from your previous courses. One of the other things is too using physical intuition or whatever tools you have to solve a problem. I'll give you an example. Let me grab grab an exam here so I can look at the problem. There was one problem on the exam. We had to find the electric potential at point P due to this rod. The charge density of the rod was this function. Okay? So we can maybe try to use some intuition to figure out what the potential is going to be at that point. Let's say I consider this dq here and this dq there. Some distance y above and below the x-axis. Okay? This charge is negative because y is negative below the x-axis. This charge is positive. The distance from here to here and the distance from here to here are the same. So that's going to tell you right away that the potential due to this term and the potential due to that term are going to cancel. And I can go and do this all the way along the rod. The total charge on this rod is 0. The potential here is going to be 0. So I know what my answer should be. My answer should be 0. Okay? So from intuition, I can determine my answer to be 0. Another way to look at it is, and a lot of people set up the integral correct. All right, because my dq was lambda dy, and my r is this distance. I forgot what I call it, a. So if you set up this integral, well, let me set up dv. Okay. And then you integrate along the length of the rod. This is an odd function, right? The square root function is even. That's an odd function. Anytime you integrate an odd function over a symmetric integral, you're going to get 0. Right? If you integrate this, the integral is going to be 0. Okay? Because if you graph this, this area and that area are going to cancel, as long as this distance and that distance are the same. All right? So, just from intuition, you can see that the integral should be 0. And so the v should be 0, either from mathematical or physical. Now, the other thing about this problem, I asked about the electric field at this point. So one of the things I want you to do in these problems is think about, use a little bit of physical intuitions. Think about what the physics behind the system. So I want to look at the field at this point through this rod. And some people said, well, because V is 0, E is 0. No, that's not true, because remember that E is minus the gradient of V, which in one dimension, that would mean in a one-dimensional world, I just write that, right? Okay. So you got to draw a picture. People don't, I don't know, a lot of people don't want to draw a picture in this class. So you got to draw pictures. So what I would do is say, okay, well, again, I'm going to use the same example, equidistant from the axis. I'm going to pick this charge and this charge. What is the field at this point due to this charge? Well, it's positive, and so it's going to point towards P. This one's negative, so this is going to point toward the charge. And you can see this is in a positive x direction, this is in a negative x direction, but both point downward. Both have a y component that points downward. And of course, I can do this for a charge over here, another charge over here, but the obvious thing is that the field is going to point straight down at that point. That's all you got to do. If you drew the picture, if you drew that picture, you'd figure out the answer. A lot of people are just guessing. Okay, so you can't do that. You have to use some physical intuition to answer questions. Just don't guess answers. Okay, because once you draw the picture, you'll get the right, I'm pretty sure you'll get the right answer. Okay, and so those are some of the things that kind of concern me regarding this exam. People are not using physical intuition or mathematical intuition. Think about what the answer should be. Just think of extreme cases. You might not know the exact answer, but think of extreme cases. But in this one, You know, drawing pictures like this will really help you. Draw pictures. Okay? Just like you have a force problem. If you have a force problem, what's the first thing you should think of?
Getting the free body on paper.
Yeah, you got to draw the free body diagram. I don't know how you can, you know, how you could get through Physics 205 without drawing a free body diagram. If you're taking statics this semester, you know how important that free body diagram is. Okay? You got to draw it. Okay? We tell you to do this because we have experience in solving these problems. We know that these are tried and true techniques that help you to solve a problem. It helps you to understand the system you're studying. Okay? So anyway, I'm hoping that the next exam, the average will be higher. I was just kind of surprised. Okay. Anyway, go over your exam. I'll send you guys the key. I'll try to send the key tonight. By tonight, you can take a look at the exams, the exam key, and you'll notice the solutions aren't very long, because these weren't very long problems. I tend to be focus more on the concepts than just having you do a lot of math, because you know, if you don't understand the concepts, you know, the math, I can give you a complicated mathematical problem. It's not going to help you. Okay, you need to understand the basic physics. Okay. All right. So today, I've lectured through essentially half of chapter 26. I want to continue on chapter 26. I did leave off talking about energy stored in fields. I want to say a couple more things. I also want to do some demos, because I haven't done any demos. And I'm going to talk about dielectric. What that means is when you put an insulator between the plates of a capacitor, what happens to it? That's going to help you do the worksheet. Okay. And I should say something about the worksheet. You could have easily done parts A and B on problem 1 on the worksheet, because all I'm having you do is plot or think about the electric potential, electric field. And I asked this question on the exam, and again, hardly anybody tried it. If I have two plates, this is positive, this is negative, we know that the field due to plates, I don't have to know I don't have to know the equation for the field due to a plate, but I should know that the field is uniform. That the field will point from the negative plate to the positive plate. Like this. And notice I'm drawing the field lines. I'm drawing a picture so I understand the problem. Okay, so I drew the field lines. I know that E, I'll do it in one dimension. It should be a partial, but I mean, we're in one dimension. Or dy, whatever. Okay. That means, and if this is constant, if I plot this, E looks like this. Now, what does the potential look like if this varies linearly? Well, we know that delta V is minus the integral of E dot dr. Okay, it's basically the area under this curve. If you integrate a constant, what do you get? Well, you get some constant times x. You're going to get a linear function. Now I'm plotting. I should be careful. I'm plotting the absolute value of v as a function of x because of that minus sign. Okay, it's going to vary linearly. That equation that I showed you. Okay. This is true when E is constant, or uniform, which is the case here. So that's what you should get for a graph. Okay, so I was surprised that nobody tried that problem in the exam because that's all you had to do, essentially. Well, though, if you insert a plate inside, then over a certain region, it's constant. Okay, in here, the potential is constant because the electric field inside a conductor is 0. So really, that's essentially what you had to draw. That was it. And then this was 45 volts. And you're going to do the same thing on the worksheet. And really all you had to do is find the equation in this line and this line. And you guys know how to do that. Okay. And in the worksheet, you're going to do the same thing. So that's why I was saying, parts A and B you can probably easily do. But part C, you need to know a little bit about capacitance. So you could have done A and B even before Wednesday's lecture on the worksheet. Okay. All right, so let's talk about what we discussed on Monday or last Wednesday regarding capacitors. We defined capacitance as the ratio of the charge over the potential difference between two plates or two conductors. Okay, and this is really called the mutual capacitance. It's how much charge you add on adjacent plates to raise the potential difference by 1 volt. There's also a self-capacitance. That's the case where we're looking at the amount of charge you have to add on a conductor to raise its voltage by 1 volt. Okay. Now when we look at self-capacitance, we really have two conductors. The second conductor is a large one at infinity. And I did the example with the sphere. And I showed you how to calculate capacitance for various geometries by really just taking the equation, deriving the equation for delta V and taking Q over delta V. That'll give you C. In calculating these, that's really all I did. And you can do all kind of geometries. If you look in the textbook or if you look in engineering books, you will see this calculated for various geometries. It's something that depends on geometry. Okay. And then I went on and said, okay, well, what if we put capacitors in a circuit? How do they behave? And we say, well, if we put capacitors in series, they add as reciprocals. If we put them in parallel, they add just add simply like numbers, like C1 plus C2 plus C3 dot dot dot. Okay. And then I did a problem that was a little complex where I had a circuit with series and parallel, and I used this equation, and that equation to figure everything out. And then I derived an equation for the energy stored in a capacitor. And so when you charge a capacitor, energy stored in the capacitor that's because work is being done by the battery. This also means that the field stores energy, just like the electric field stores energy, just like the gravitational field. So let me do a demonstration showing you how the capacitor stores energy. So I have here actually I should. Let me get rid of the PowerPoint. Okay, that display is strange. Hold on a second. Okay, let me get rid of that. So here's I have a little circuit. So I have a light bulb, and I have a switch and a battery. So I'm going to connect my switch so that I have current going through here. Okay, so I have electricity flowing through this capacitor and through the battery, and what I'm doing is I'm charging the capacitor. This is a special type of capacitor. It has a material in it called aerogel. It's actually 1 farad. It's very unusual to have a 1 farad capacitor. That's a very large capacitance, and it's the dielectric material that I place in between the plates that makes the capacitance 1 full farad. Okay? I'm going to take the switch, I'm going to disconnect from the battery, and I'm going to connect the bulb to the capacitor to show you the energy that's stored in the bulb. I'm sorry, in the capacitor. And you'll see that the light's on. And you'll probably see that it's going to get dimmer and dimmer as we go along, because the capacitor is not like a battery, right? Because the capacitor will eventually lose all of its energy. It's dumping its energy into the light bulb, and you might already be seeing, I can see it, that the light bulb is getting dimmer and dimmer. Okay, can you guys see the fact? Can you see that the light is getting dimmer?
Maybe just slightly. It's not obvious, but
it's hard on it
makes sense that it would.
Yeah, I mean, you're right. I mean, now it's a lot more dimmer. Maybe.
Yeah, now we can. There's a definite difference now.
Okay. Let me try with something else just to show you. And this time I'm going to dump energy a lot more quick, a lot faster. Let me charge this up. I'm going to charge the capacitor up real quick. Okay. And I don't know how familiar you are with these things. These are flash bulbs from old cameras. I'll just show you. Just to show you how old these are. Look at how old the ad is. Okay. These are very hard to get because they don't have cameras that flash bulbs anymore. Okay, so now I'm going to dump the energy from here into the flash bulb. Here we go. Okay, for me, I'm seeing blue right now because I'm right next to it. For you guys, it's probably not the same, but I dumped all that energy in a very short time. This thing is very hot. Okay, so I dumped a lot of energy into it, and you saw a bright flash, right? Okay. So that shows you that the capacitors store energy. Here's another example of a capacitor that's pretty large. This is 0.47 farads. Let me show you the inside of a capacitor, what it looks like. This is a smaller capacitor in terms of how much energy it can store. But these are just basically 2 sheets of aluminum foil rolled around in the cylinder, and in between the sheets there's an insulator. That tannish, that material is the insulator. That's all they are. That's all capacitors are. Okay. If you took this apart, you get a really long roll of aluminum foil. Okay. That's all it is. And they're used to store energy. So let me show you another one. This is a big one. And you notice that I shorted the terminals. That's because the terminals can get charged. On this one, this is a big capacitor. If the terminals get charged and I touch it, it'll probably kill me. So I have to make sure that the terminals are discharged. Okay. So handling big capacitors is very dangerous. Here's another dangerous one. Again, the terminals are shorted. Okay. Your air conditioner has a capacitor. Your central air conditioning system has a capacitor in it, and that one's fairly dangerous. If you try to replace it, it's a $20 part, but the person who comes in and replaces it charges like $400. Okay, but if you learn how to replace it, that's the first thing that goes usually in your central air is that capacitor.
Yep, I did that 2 years ago.
You replaced it yourself?
Yep.
Okay, yeah, and so you spend about $20 as opposed to $400.
Yeah, it's super cheap.
Yeah. These are called student capacitors. And again, let me zoom in a little bit. When you're on campus, we do a lab with capacitors. So these are our student capacitors. You can take them apart. They have insulators on them, so I can keep the plate separated. These are just little pieces of insulator. And I can measure the capacitance of this thing very easily. I have a capacitance meter. In fact, let me get up closer. This capacitance meter has been acting kind of strange, so. I don't know why this is acting so weird. Just give me a second. Anyway, this thing's it's been acting up. I don't know why. I'm getting a different value for the capacitance as I did about 20 minutes ago. Okay, so I mean, you can measure the capacitance. These are nanofarads. So just to give you an idea, this is a capacitor. It's around 1 nanofarad. This one's half a farad. And the difference is the insulator I put in between the plates. Okay. So this is what students use when we're in the lab. I was going to actually do series and parallel connection with these, but then my I don't know what's going on with this thing. It's acting very strange. The results I'm getting don't make sense. I don't know if the battery's almost dead or what. So I will not make any measurements with it. I have one more thing I want to show you. I have here, and I have to move some things around, sorry. I have a capacitor here. We also use this in the lab. We use this in the lab to prove this equation of, oh, I can't see it. The epsilon naught A over D equation for the parallel plate capacitor. Okay, so this is just a parallel plate capacitor, and we use it in the lab to actually verify the equation you derive for a parallel plate capacitor. And I want to illustrate how capacitors store energy. And I want to look at the charge on the capacitor. But you got to think carefully about what I'm doing here. Okay? This device here is called a Wimshurst generator. It's actually it's scarier than the Van de Graaff. This hurts more if you get shocked by it. I've been shocked by it. It hurts more than the Van de Graaff. Okay? So I'm going to rotate this. And I'm going to charge the capacitor, and I'm going to use the electroscope to look at how much charge I have here. Now, what happens when I change the plate separation of a capacitor? Now, remember, capacitance for a parallel plate capacitor C is epsilon naught A over D. Hold on, let me write it further down. Okay? So if I increase D, the capacitance decreases. If I make D smaller, the capacitance increases. Okay, so let me charge things up. Things always work better when I'm not in class. My electroscope is not really moving at all. So let's do this. Nothing's happening. Let me try one more time. I know my electroscope, my WIM source is working because my second monitor is blinking on and off. Okay, let me keep charging this. Not sure why nothing's happening. Okay, let me increase the plate separation. Let's see if this electroscope's deflects. The deflection changes. Do you see the deflection changing on the electroscope?
It's slight, but yes.
Yeah, I don't know why it's just slight. It should be more than that. If I go back, it goes back to the original position. Now here's my question. I'm increasing the plate separation. I'm decreasing the capacitance. Why is that deflecting more? And here's the reason. What happens to the charge on the capacitor? Where does it go?
It goes nowhere.
Well, it's connected to the electroscope, right? I have wires that go to electroscope. What happens is the charge goes to electroscope. So when I increase the plate separation, the capacitance decreases. It can store less charge, and all the charge goes to electroscope. And when I increase the capacitance, the charge goes back onto here.
It's distributed evenly between the two.
Yeah, so
Are you being serious?
do you see it move? When I did it on, I think I did this last Tuesday. It was way more dramatic. This thing was like at 45 degrees. Okay. So anyway, so this shows you that this thing is getting charged, and it's storing energy. So when I have the plate separation close, all the charge that's on this thing goes to the capacitor. And when I increase the plate separation, the charge that's on the capacitor goes to the electroscope. Just to show you how how much energy the Wimshurst generator can store. It also has capacitors on it. Let me move back a little bit because I don't want to damage my computer when I do this. It does work by induction. So I'm going to put these levers down. That allows these capacitors to charge. Hopefully I can get this to work. It's not working that great. Did you hear the click? Yeah, okay. It worked okay, but you can hear the clicking sound. That's when it's arcing. That's when it's so much charge is built up, it starts to discharge. The only problem I have is this is not working very well. Do it one more time. No, it's not working that great. I usually can get a much bigger arc, much bigger spark, but it didn't work that well today. Anyway, I just wanted to show you some demonstrations of what capacitors look like and how they behave. I'll have others. Okay, so let me fix the monitor here, or the display. So let's do a quick kind of a review problem involving capacitors. Uh-oh, what happened? Suppose we have a capacitor. Just to review. Parallel plate capacitor. And we charge it. With a battery. Okay. Then we disconnect the battery. And we increase the plate separation. What happens? Well, what happens to the charge, first of all? Charge
in this case, can't go.
Can't go anywhere, so charge stays the same. So what does that mean? What does that imply about the electric field strength?
Decrease?
Well, Q stays the same, A stays the same, so an epsilon naught doesn't change, so it stays the same. Okay. What happens to the capacitance? If I make D bigger.
It's going to drop.
Okay, it goes down. What else do we can we look at? The voltage. What happens to the voltage? Well, if this decreases, this stays the same. What must this do? And I shouldn't say voltage. I should say the potential difference. What happens to this value? This stays the same. That decreases, so this must increase. Okay, so let's look at the energy stored. If this stays the same and C decreases, what happens to U? This stays the same, this gets smaller, U has to get bigger. U increases. Okay? It's harder to see it with the, well, you can see it with this one because Q stays the same, V increases, so U increases. It's hard to see with this one because this will decrease with D, but this will increase with D squared. So U will increase by a factor of D. Okay. What I want to do now is I want to derive this expression a different way because I want to show you another way we can calculate capacitance. We left off the other day talking about energy. We said that this is the energy stored in a capacitor, but we also said something a little more general. We looked at the following. We look at the energy stored in a parallel plate capacitor. And we got this equation. And basically, the A is the area of the plates, D is the separation of the plates. This is the volume between the plates. So this is equal to okay, volume between the plates. That's an abbreviation. Okay, so then we define U over the volume to be the energy density and we said this is true in general that the energy density in the field, in the electric field, is given by this expression. The energy per unit volume stored by electric field is given by this. And I said this is true in general. I did this for the parallel plate, but one can show that this is true in general. And so one can write the energy stored in the field is equal to the integral of little u dV, where V is the volume. Furthermore, we can say U is the integral of 1/2 epsilon naught E squared dV. And the limits of integration are over the region in which this is valid. The expression for E is valid. And so what I want to do is calculate the energy stored by the electric field produced by a conducting sphere. Of course, this is also equal to Q squared over 2C. So then I can use this to calculate the capacitance of the sphere. So I want to use this equation. Well, if I have a conducting sphere, with charge Q, radius big R, I'm out here. What is the electric field at this point in space due to that conducting sphere? And this is something people didn't understand in the exam, is that if I'm outside the sphere, I can treat the sphere like a point charge. And so the electric field outside it, the magnitude of it, is K Q over R squared, where R is the distance, P is from the center of the sphere. Because of its spherical symmetry, you can treat a sphere like a point charge when you're outside the sphere. Okay, so then I'm going to go into this equation and say, okay, I'm going to integrate this. So E squared is going to be KQ over R squared dV. Well, now what's my dV? I'm integrating over a bunch of spheres. I'm integrating over the volume of a sphere. And so this is the surface area of a sphere times dr. Okay? So I have, think about this, the dimensions. Okay? Distance squared times distance cubed. Volume is a distance cubed. Oh, this is squared, sorry.
I was just about to ask. Thank you.
Okay, sorry about that. Okay. So let me simplify this. And now I got to say something about the limits of integration. What are my limits of integration? Well, it's over the region in which this field is valid. Where is this field valid? Well, it's valid from the surface of the sphere all the way to infinity. Right, the electric field is valid from outside this sphere. This equation is valid from the surface of the sphere all the way to infinity. So let me pull out some constants. This integral is not hard. Of course, the limit up here is 0, right? 1 over infinity is 0. So then this is just going to give me 1 over r. Okay. I lost something. I lost an epsilon naught. I lost an epsilon naught everywhere. All right, so what is this? Oh, this, and I forgot a square. It's very sloppy today, sorry. What is 4 pi epsilon naught?
It's K.
Or 1 over K,
1
right?
over K.
Okay, so I can get rid of one of the K's here. There's too many K's. Let me check I'm checking my math. Hold on a second. Oh, I'm fine. We're fine. Okay so far? That's the energy stored in capacitor, kq squared over 2r. But, so this is okay, but this is equal to q squared over 2c from this equation. So the q squares cancel, the 2's cancel, and I get 1 over c equals k over r. So c is equal to r over k. So c is 4 pi epsilon naught r, which is the same as what I got the other day, but using a different method. Now granted, deriving this equation using this method is probably not very useful because I got this expression really fast using the other method. However, there are some cases where using the method I used the other day to calculate capacitance is really difficult. And it's much easier to solve for C using this method. They have really two methods of calculating the capacitance. And you just choose the one that's easier for you, given your geometry. Remember, capacitance is a quantity that depends on geometry of the system, the size and shape of the material. Okay. So let me do an example involving 2 capacitors. Suppose I have 2 capacitors and I charge them up. So I have a 200 picofarad capacitor. Charge it up to 2,000 volts. I take another one. That's 800 picofarads. And I charge it up to 2,000 volts. So they're both charged to 2,000 volts. fact, let me make one red, just out of simplicity. Actually, no, let me not do that. I disconnect them, and I connect them together. So I take the 200 picofarad capacitor, that's charged at 2,000 volts. So this is at 0 volts, this is at 2,000 volts. This is at 0 volts, this is at 2,000 volts. And I connect it to the 800 picofarad capacitor. So I take the positive terminal of this capacitor and I connect it to the positive terminal of this capacitor. I take the negative terminal of this capacitor and I connect it to the negative terminal of this capacitor. What happens?
Will the energy stored within them try to redistribute itself evenly?
Okay, well, redistribute. So let's see. So the charge is going to change then, you're saying, on each capacitor. So what I'm doing is I'm taking a plate that's at 2,000 volts and connecting it to another plate that's at 2,000 volts. And I'm connecting them to a wire. Is there going to be electric field in the wire?
The potential is the same, so no.
No. So there's no charge going to flow here. The other side, I have a plate at 0 volts and another plate at 0 volts, and I'm connecting them together. Is any charge going to flow between these two sets of plates?
Nope.
No. So nothing's going to happen. Everything's going to stay the same. No work is done. The capacitors, each capacitor has the same amount of charge on it. The total charge is the same. Nothing happens. It's a boring system. Right? This is the charge sharing problem we talked about the other day. Okay? Now let me change the problem. Let's say I take this plate of the capacitor and I connect it to this plate of the capacitor. So now I go this way. I do that. Now charge will flow because this plate and this plate were originally at different potentials. Charge will flow here and here because these two plates were at different potentials. One's at 0 volts and one was at 2,000 volts. So charge will flow. Charge will flow until both plates are at the same potential. It's the charge sharing problem. Okay? So charge will flow until this potential difference equals this potential difference. And the initial charge I had is going to have to be equal to the final charge I had. So what's my initial charge? Well, I'm taking this plate and connecting it with this plate. This is positively charged. This is negatively charged. In fact, how much charge is on this capacitor on each of the plates? How much charge is on each of the plates? I got to take 2,000. So Q1 is 2,000 volts times 200 picofarads, whatever that number comes out to be. The charge on this one is 2,000 volts times 800 picofarads. So the total charge I have between the two plates that are oppositely charged, Q initial, is going to be and this comes out to be 1.2 microcoulombs. That's how much charge I started with when I connected positive to negative, negative to positive. Because one's going to have this amount of a negative value of this charge, and one's going to have a positive value of this charge. And in the other case, this is going to be negative and that's going to be positive. And so the total charge is going to be the difference of those two numerical values. So this is the charge sharing problem. And so charge will flow until they're both at the same potential. So this is not going to be the case. But we know delta V final, the potential difference between the two, is going to be the same. And the total charge is going to be equal to this. So delta V final is 1.2 microcoulombs over C1 plus C2. Which is 1,000 picofarads, which is 0.001 microfarads. So this comes out to 1,200 volts. So the final potential difference is going to be 1,200 volts. So how much does the energy change? How much energy do I have now compared to what I started with? In other words, what's the change in energy? I want to know delta U. I want to know U final minus U initial. How much energy did I start with? Well, I started with 1/2 CV squared right? Remember, the energy looks like this. You can write them either one of those ways. So I'm writing it this way. U final let me use my other black marker. If you actually do the calculation and you find U final minus U initial, the energy has decreased by 0.00128 joules. Or 1.28 millijoules. Because when you do this calculation, you got to convert the picofarad to farads. But I don't want to go through all that work because it's going to waste time. Questions on this? So energy is lost. Where's the energy lost? Because what happens is the wires have resistance, and so when charge flows through here, energy gets lost. Okay. Resistance acts like friction, and we'll see that when we do chapters 20, when we do 27 and 28. Okay.
So is that a conversion to heat?
Yes. Yeah, that's true. Okay, so now let's look at what happens. So I like this example. There's a lot of problems in the book on charge sharing. I like them because they help you to better understand the materials from 23, 24, and 25. And all these problems I do with charge sharing and saying, you know, what happens when I disconnect the battery and change the plate separation, that actually helps you go over the materials from 23, 24, and 25. So I like those questions because I know the material is a little bit hard to sink in. So I try to do things so you end up going over them again. Suppose we take a parallel plate capacitor and we insert an insulator in between the plates. What happens? So you can do an experiment for this. Okay? You get parallel plates. And we insert something, an insulator. So we charge the capacitor, we disconnect the battery, and we insert an insulator. So what happens? It turns out if you do an experiment, the voltage decreases. Something happened to my display. Your display is okay. My computer, the slab is black and yours is red. That's just strange. Okay. So we put the slab in, and what happens is delta V decreases. So the potential difference decreases by some factor. We're going to call kappa. And this is called the dielectric constant. Okay, so it decreases by a value of kappa. So what does it do to electric field? Well, that means then that if the potential difference decreases by kappa, remember, battery's disconnected. Battery's disconnected, we insert the slab in, the potential difference decreases by a factor kappa. So delta V final is delta V that we started with over kappa. The charge stays the same on the plate, but charge can't go anywhere. So if the charge can't go anywhere, and we know that capacitance is Q over delta V, if this decreases by a factor of kappa, Q stays the same. This means C increases by a factor of kappa. So the new capacitance has increased by a factor of kappa. So that means that C equals kappa C naught, where C naught is value of capacitance with empty space between the plates. Okay. So you increase the value of the capacitance by kappa. So for a parallel plate capacitor then, where you put the slab in between, the capacitance increases by a factor of kappa, and your expression is this. So all the capacitance values increase by a factor of kappa. Now I'm going to say something about the dielectric material, the insulator. It's a nicely behaved material. Okay, there are some capacitors, there are some dielectrics where V doesn't change linearly, but a lot of them do, and so I'm going to focus on those. There's some anisotropic materials where epsilon has to be, the epsilon has to be written as a matrix. We're not going to deal with those. And so this term now, we can define something called epsilon, where epsilon is called a permittivity. It reflects how the field lines can penetrate a material. Epsilon naught is the permittivity of free space, the permittivity of empty space, but epsilon is the permittivity in the material, whatever the material is. And this is going to be dependent on what a kappa is, right? So what are the advantages of putting a dielectric in capacitor? One, it increases capacitance. Two, it increases the maximating operating voltage of the capacitor. And three, it provides mechanical support of the electrodes. Okay, so those are the reasons why you want to you use dielectrics. It increases capacitance, it increases the maximum operating voltage. Not always, though. Depends on the material. And generally, and provides mechanical support. For example, these capacitors that are my good one disappeared. This 1 farad capacitor that I had, its maximum operating voltage was 5.5 volts. Okay, which is not much. All right, that's because of the material and how close the plates are. Some of them are rated at higher voltage, like this one's rated to 200 volts. And the big one I had, this guy, was rated at 2,000 volts. This thing can store a lot of energy. Think of 1/2 C delta V squared. This thing could store a lot of energy. And that thing discharges through you, you're in trouble. Now, all materials, I said this earlier in the class, in the course, have a breakdown voltage, a breakdown field And if you put a high enough voltage across an insulator, it'll break down and it'll conduct. Of course, you can look up that material. And if you look in the table in chapter 26, table 26.1, you'll see the breakdown voltage, fields for various materials. Sometimes we say breakdown voltage, but that breakdown voltage depends on the thickness of the conductor because really it's the field you're interested in. There's different types of capacitors. There's dielectrics. You can put a paper in between the plates. You can make a variable capacitor. Those are metal plates that are interwoven with the air gap. Old radios had those. You have oil capacitors for high voltage applications. We have one on campus. I can't bring. I can't, if you guys were on campus, I would show you nice oil ones. When those things blow, those are pretty bad. And then the electrolytic capacitors. These are just plates in an ionic solution. And those are polarized. They have a polarity. And if you hook them up backwards, they'll pop. I think this one. This was the electrolytic capacitor. So you don't want to hook this up wrong. They all have various characteristics. I mean, I have a whole box of capacitors here. Okay. You can buy capacitors, and they're optimized for various applications. So, why does a dielectric reduce delta V in between the plates? So some things you need to remember, that the dielectric materials consist of molecules in which the centers of charge won't coincide. Basically, when you put an insulator in between the plates of in between the plates of a capacitor, you're going to form dipoles. Okay. Some dielectric materials are polar, some are not, but either way, when you put them in between here, you're either going to align the dipoles if the material is polar, or you're going to form dipoles along the direction of the electric field. So here's a picture showing you, first of all, the electric field between the plates and the dipoles being aligned. Those dipoles, though, when they align, they're going to create their own electric field in the opposite direction of the field between the plates. So what happens is the dipoles produce a field in the opposite direction, and so the total field is reduced by a certain value. Okay? So the total field in between the plates has been decreased. So if these are the field lines between the plates because of the plates, the dielectric will produce one in the opposite direction. And this is an induced field. And so that the total field is the difference between those two. Actually, E-induced is not the best term to use. A lot of physicists use bound because this is the field due to the charges that are bound to the material. Because we're going to talk about induced electric fields later, so that might be confusing. And this is going to be equal to, for parallel plates, that, because, let's write it like this. Okay. So then this is going to be sigma over epsilon naught minus sigma induced over epsilon naught. And really, it's bound. I should say bound, but that's okay. So sigma induced over epsilon naught looks like that. Furthermore, if I cancel out the epsilon naught, sigma induced is sigma times 1 minus 1 over kappa. If a dielectric is replaced with a conductor, E is 0 here. What does that mean? What does that make kappa for a conductor? If the field in here is 0, what's kappa for a conductor? These two have to be equal, so kappa is equal to infinity. Kappa equal 1 for empty space. So let me show you a picture.
What you just wrote is cut off by the slide.
Oh, it's cut off? Okay.
Yeah, I can't see it.
All right, let me fix that.
Cool, thank you.
Okay. So let me quickly show you this slide. So just a simulation, simulate what happens. Suppose you have a dielectric in an electric field. The first picture just shows you the electric field and the dielectric. But then the charge in the dielectric rearranges itself. You form dipoles. And so now you see the original electric field and the field due to the dipole separately. Now we're going to add the two together to get the final results. And so that's what the field looks like. And so you'll notice that the field lines don't fully penetrate the material. So the bigger kappa is, the less likely the field lines are going to pass through the material. That's why I'm saying kappa represents how the field lines will penetrate the material. The bigger kappa is, then the less the field lines will penetrate the material. Okay, but before, so I want to do one more thing. I'm going to do this next time. I want to talk about the following example. Hold on a second. I want to talk about this. This will help you a little bit with the worksheet. Suppose I have a capacitor and I stick a dielectric in it. I'm going to look at two different cases. Okay? By the way, I have a video of this particular problem solved in gory details. And I'm not going to go through all the gory details, but I'm going to go through some details next time. Okay, so let me do this. Let me do the two cases. Let me do the following. Let me charge this capacitor, and then we will put the slab such that it takes up half the volume. So we charge it. Disconnect the battery, and then stick in this dielectric so it takes half the volume. The charge ain't going to go anywhere. Well, what happens? What's going to happen when I stick this in? Well, the total charge is going to stay the same on each one of the plates. But what happens to the charge? What's going to happen to the charge when I insert the dielectric?
Intuitively, I feel like it's just kind of moved towards the right side.
But you're saying it's going to rearrange.
Yeah.
Okay, you're right. So the charge here will rearrange itself. So you're going to have different charge on the left as the right. So whatever this Q was, that must be true. You're going to have different charge here than here. What about the electric potential? We know that in here, the field is constant. We know the field in this, everywhere here is constant. That means V changes by the same amount as you go from this plate to this plate. Isn't that true? And of course, the field's still going to be uniform here. But what can we say about the field here as opposed to the field here? You might say, well, the field here is different from here. But be careful, because let's look at an equipotential. Okay? Let's look at an equipotential. So it's a line like this. It's perpendicular to the electric field. What happens to the potential as you go from this side to this side? What do we say about equipotential, potentials at a boundary? The V can't change at a boundary. So the V all the way across here is the same. If this is another equipotential, this has to be the same all the way across. If this is another equipotential, it has to have the same V all the way across. So that means that the potential difference between here and here have to be the same. You actually have two capacitors, this one and this one. You can treat this as two capacitors in parallel. The delta V of this capacitor is equal to the delta V of this capacitor. This capacitor is one of half the total area, and this capacitor is half the total area. But you have two capacitors in parallel because the V has to be constant here. The V has to be constant here. As opposed to this case, Your equipotentials look like this. You can have the electric field change in here because the electric equipotentials are in this direction. You can have V to go be different here and here because this is along one of the equipotential lines. Okay? And so in this particular case, this potential difference is different from this potential difference, is different from this potential difference. These act like you have three capacitors in series. This delta V is different from this delta V is different from this delta V. However, the Q here are equal and opposite. The Q here and the Q here are equal and opposite. The Q here and the Q here are equal and opposite. So these are three capacitors in series. This acts like two capacitors in parallel. Of course, each one has half the area. So this is kappa epsilon naught A over 2. And this one is epsilon naught A over 2D. I have a video I created that goes through all the gory details of this problem. It's on Canvas. You should watch that. I'm going to cover this problem on Wednesday, but I wanted to say some stuff here because I wanted to help you do the work, finish the second part of the worksheet. And so the electric potential, it kind of looks like this for this one. If you plotted V as a function of X, then it's going to go up at some rate, but then the field decreases, so the slope changes. Just something like that. Of course, on the worksheet, you have to figure out what those numbers are. Here, if you plot V as a function of X, looks like that. Where X is in this direction, okay? Questions on that?
It got a little, the camera is just a little bit blurry. Can you tell me what the epsilon naught expressions on the bottom left of the screen are?
Oh, okay. Let me
Those
rewrite
two,
this.
yeah.
So this is the capacitance of the left side, kappa. Epsilon naught, half the area, divided by D. And this is the right-hand side, epsilon, A over 2, divided by D. So this is C left, and this is C right. And the sum of those two is the total capacitance of the system. Whereas here, the total capacitance is this capacitance plus this capacitance plus this capacitance. But they go in series, so it's C to the minus 1 plus C to the minus, let me rewrite. C1 to the minus 1 plus C2 to the minus 1 plus C3 to the minus 1, and then you take the reciprocal of that to get the total capacitance. And the reason why we say that is because this delta V, and this delta V, they're all different. Does that make sense?
Yes, thank you.
Okay. So I'm going to stop here because I went a little bit went over quite a bit. So Wednesday, I'll do a couple more examples. Like I said, there's a long video on this problem. I really go over in a lot of gory details. It's a good problem to understand, try to understand. Okay.
And we have everything we need to finish the worksheet now.
Yes. Yeah, so A, B, one A, B, and C should be pretty easy. The harder one is going to be finding the V's for this one, but it's not that bad. Okay. All right, so we'll see you on Wednesday.